Good afternoon and welcome back to Module 7, Organic Chemistry. In our recent few lessons, we have been looking at the properties of alcohols, and one of those properties is the amount of energy that burning these can produce. And we've recently also calculated the molar heat of combustion, looking at the variety of different alcohols and how much heat they actually produce. The combustion of alcohols and other fuels is a type of oxidation reaction or redox. So remembering back to year 11 when we looked at redox reactions. So our alcohols can also be oxidized by some oxidizing agents. And in class today with our oxidation prac, we tried to oxidize our alcohols, both a primary, secondary and tertiary, with potassium permanganate, and that is an oxidizing agent. Another oxidizing agent that can be used is potassium dichromate, but we chose not to use this in class due to some of the risks associated. Now, the products that can be produced from these oxidation reactions will depend on the type of alcohol that we have. So in our experiments, we're looking at a primary alcohol. We looked at 1-butanol. A secondary alcohol, we looked at 2-butanol. And then we looked at our tertiary alcohol that we had there, which was our methyl propanol, if I am correct. So what we're going to get is depending on where that functional group is. So our primary alcohols first will oxidize to form aldehydes. After they've oxidized to form an aldehyde, further oxidation can occur, and that will then form the corresponding carboxylic acid. With our secondary alcohols, they will oxidize to form ketones. And our tertiary alcohols are resistant to all oxidation by an inorganic oxidizing agent, so they don't normally react. Now, we are looking at the nomenclature of each of these different functional groups as we come across them, and obviously some of these groups are foreign to us. So our aldehydes, our carboxylic acids, and our ketones. So we will next look at the different groups and what they mean. But for the moment, we'll continue going with our oxidation. So in this example here that we can see on the board, this is our general equation for what happens to primary alcohol undergoing oxidation. And we can see here our general formula. We can see here that this is the terminal or end carbon with our a hydroxyl group off the side here. This R chain is the rest of the hydrocarbon group. So you can see here we have our reaction with our acidified dichromate, so that's what the H plus is for. In the reaction we did in class, we used permanganate, and it will then form an aldehyde. So that aldehyde then is still our hydrogen off there, but this part of the reaction is changing to a double bond with our oxygen. With heat now applied, then that will progress further to form a carboxylic acid. Again, looking at the difference end here on our functional group. So let's have a look at an example. These are with propanol. So in our first one, we've got propan-1-ol, so it's obviously a primary alcohol with our OH on the end. By it being oxidized, we are then getting this change in our functional group here on the end, and this is indicative of an alkenyl group or our aldehyde group. And so you can see there with its name now, propanal. So we've gone here single bond to our and our hydrogen, and now we've got that characteristic double bond to the oxygen. And if heat was continued to be applied, we could then continue that oxidization process and form a carboxylic acid, and in this case it's propanoic acid. So again, we still now see the presence of that double bond with the O, and the oxidization, we're getting that extra oxygen forming there with the hydrogen on the end. We'll discuss this a little bit further in class. This will be just a summary, and it'll make a little bit more sense also when we talk about our naming and what happens there. Now, what would happen if we wanted it to stop at that aldehyde? What if the product that we wanted was the aldehyde and we didn't want it to continue on to the carboxylic acid? Then we need to change our conditions. So you'll notice in the previous slide, we can see that here heat is applied. So obviously, if we lower the temperature so that heat is not there, and even a shorter reaction time, if we change those conditions, then that can be stopped at the aldehyde stage. And if we actually distill it and remove it from the reaction mixture, that way then we're preventing it from being oxidized further. Now, also in our experiment today, we did look at secondary alcohols. And so when they are oxidized, again, they form a different functional group again altogether. So again here, the difference here is we've got our functional group now on our secondary carbon, so not the terminal ends, but inside the hydrocarbon chain. And you'll notice here we still have the hydrocarbon chain and the hydrocarbon chain here. All that is changing here is this hydroxyl group, again, is going to a double bond O. Now, if we go back and look at our previous slide, we can see here that we still have that double bond O. The difference between that aldehyde and that ketone is the functional group is the same, but its position is different, and that makes a difference in its properties as well. So this is our general equation here. Again, if it's using an acidified oxidizing agent. So let's have a look at an example here. Now this one's with propan-2-ol, so the 2 indicating that it's not a primary alcohol but a secondary, and we are adding our oxidizing agent there, and what's happening here is we still have our hydrocarbon change, our CH3 here and our CH3 here, indicative by these areas over here, but this hydroxyl group is being changed and oxidized to form that double bond to the oxygen atom there. Now, what happens with our tertiary alcohols? Today in class you would have noticed our tertiary alcohols didn't change. So tertiary alcohols are actually resistant to the reaction with acidified oxidizing agents such as the ones we used in class. So what actually happens is that increase in the number of carbon to oxygen bonds and a decrease in the number of the carbon to hydrogen bonds, what happens is the carbon attached to the hydroxyl group doesn't have a C to H bond to break, and because there is no C to H bond to break, that oxidization can't actually occur. So we'll practice some of these a little bit more in class. I'll get you to take some notes and read your textbook on this relevant section. And we're going to go back now to naming our functional groups, including our aldehydes, our ketones, and our carboxylic acids. Talk soon.